it looks like here we have the absolute value equals a linear equation. Now, this is new, but really doesn't change anything, really. We still have to consider that this inside, to undo this absolute value, we need to consider that this could be the positive version, or this could be the negative version. Now, because we don't really know x, it's a little bit harder, more challenging to figure out, but we don't really need to figure that out because we can just always check for extraneous solutions here. Okay, so let's try this then. So we can consider our positive domain problem where we have the inside equals, and let's just say that this is the positive version. Okay, and then the negative version must look like this. The inside is equal to the opposite of that. Now, the textbook actually, if I'm not mistaken, I think they actually put the negative on this side, but that's okay. It doesn't really matter which side the negative's on. We can just make this the opposite sign and then make it equal to positive. But either way, we'll end up with the same solution. So once I've established the two possibilities, the positive and negative possibilities, I'm just going to go ahead and solve it algebraically. So I'm going to subtract x from both sides. I'm going to subtract 2 from both sides, and I'm going to get 2x equals negative 7. So x is equal to negative 7 over 2. Okay. Before I test it, I'm going to just solve the other side here. So I'm just going to add 3x. Maybe I'll get rid of the brackets first. I'm going to add 3x to both sides, and I'm going to add 5 to both sides, and I'm going to get x equals 3 over 4. Okay, so I've isolated the absolute value, I solve for the plus and minus, and I have to check solutions. Okay, because there is a possibility, we've seen that it's possible that we get extraneous solutions. Okay, so here I'm going to test x equals negative 7 over 2. When I plug it in, I'm going to end up with, this is negative 3.5. So I'm going to end up with negative 8.5 absolute value is equal to, well, negative 3.5 times 3 is negative 10.5 plus 2. Okay, when I plug that in, I get 8.5 equals negative 8.5. That's not true. That's extraneous. Okay, so let's test x equals 3 over 4. When I test x equals 3 over 4, I get negative 4.25. Okay, 3/4 minus 5 is negative 4.25. Here I'm going to get 3 times 3 over 4. Well, 3 times 3 over 4 is 2.25. Plus 2. This becomes positive 4.25. Equals positive 4.25. Well, this one happens to be perfectly good. Okay, that one works. Okay, so it is important to check solutions. Now, you may be asking, well, why is there only one extraneous and the other one's good, whereas before they both were extraneous? Well, let's take a little bit closer look at this. Okay, so if I were to think of what this looks like, and you can go ahead and graph this too on your Desmos. But if I were to think about what this looks like, the vertex of the left-hand side, so I'm just going to graph it in purple here. This, if I were to graph that, that's a V-shaped graph that bounces at 5, right there. Okay, and if I were to graph this other portion here, 3x plus 2, maybe I'll choose a different color. Choose blue. If I were to graph 3x plus 2, well, that's a linear equation with slope of 3 and a y-intercept of 2. So it's here, and it's a bit steeper like that. Okay. Well, there clearly is only one intersection here, and that's our solution of 3 over 4. That's the good solution. Now, we could even justify the extraneous solution because this solution, this is a steep graph, slope 3. This part of the absolute value is a slope of 1. And if I were to extend this back, remember that the absolute value is a piecewise function where it's described by a linear equation, but it's only good up to here. But if we let it go, keep on going, you can see that, well, that if there were to be an intersection, which doesn't actually exist, this intersection here happens to be at negative 3.5. So this is the solution that happens outside the domain restriction. Okay, and it's an extraneous solution because it's outside of the domain of this line. But if we were allowed to, it gives us the extraneous solution of negative 3 over 2, or negative 3.5, which is negative 7 over 2. So we can actually justify both the solution that is real, right there, and the solution that doesn't exist, which is right there. Okay? And the shapes of the graph help us justify this.